Okay, so it's a great pleasure to be here, the place where the modern science was born, basically. So the lectures that I will give are about tensor networks. They will mainly be focused on quantum aspects of tensor networks, but as you will see, the classical and quantum, they all go through each other, and it's all very very similar. So the lectures, so there's 4 lectures of from today till Friday, and the lectures will probably the complexity of them will increase linearly as a function of time. Okay, so that means that in this lecture there will be very basic, a very simple introduction into motivating actually why tensor networks are useful and why you should be interested in looking at this, or why actually the problems that are posed in statistical physics and quantum mechanics or quantum many-body physics are very well amenable to this description in terms of matrix product states and tensor networks in general. So the plan is to today to give a very basic introduction, talk a little bit about Hamiltonians, about what is it actually that you want from Hamiltonians, like why are you interested in the ground state, what are excited states, what are the properties that a ground state has to satisfy, a little bit about area laws for the entanglement entropy, many related things, and this will motivate actually the construction of these tensor networks. So then in the next lectures, or if kind of things go very fast, and we can already do this today, is we'll talk about the manifold of matrix product states, basically the technical aspects of the tensor networks, how to define somehow something as called the time-dependent variational principle, how to understand what does it mean actually an excited state or an excitation on top of the ground state. We will all do this both in 1 and in 2 dimensions, in somehow quantum dimensions, or of course the same kind of things can be done for the classical case in a very kind of parallel way. Then the third lecture will focus on phases of matter. So it turns out that these tensor networks are extremely useful to classify different phases of matter, and we'll have to be a little bit careful in how to define this. What does it actually mean, a phase of matter? How do you adiabatically? So this basically, and colloquially, it means that there's no adiabatic way of going from one phase to the other one without going through phase transition. How do you define this, and how can you actually use matrix product states or these tensor network states in general to make progress into that in that question, and really kind of understand that indeed there are topological obstructions for going from one phase to the other one. And it turns out that indeed all of this this formalism in terms of tensor networks is basically a new language for doing many-body physics. It's where you focus on the correlations between the different particles or the different kind of entities, as opposed to the global probability distribution or the global wave function. It turns out to be actually it gives you exactly the right technical ideas for being able to solve this and for observing these obstructions. So one of the reasons that people in condensed matter and statistical physics are so fascinated by systems that exhibit topological order is because they seem to violate this whole Landau paradigm that different phases are characterized by different order parameters. Okay, that there's basically some symmetry breaking going on, and these tensor networks make this very clear that even if you have a topological phase transition, there's still some kind of symmetry breaking going on, but it's of a much more subtle way. It's namely a symmetry breaking in the way the entanglement is distributed in the system, and that's what we will talk about in the third lecture, or the second, depending on how fast all these things go. And then somehow in the last lecture, we want to take this a step further and kind of dig very deep into this in topology pieces of matter, topological quantum field theories, lattice versions of that, and also some very nice connections with conformal field theory. That all of these different tensor networks actually give you, in many ways, they give you the representation theory for tensor fusion categories. And for the people that are familiar with topological quantum field theory, conformal field theories, there is indeed, this is well known, that the tensor fusion category is underlying somehow both of these things, and tensor networks make this actually makes this very explicit how these are connected to each other. So please interrupt me anytime that something is not clear or if you disagree, because certainly there's many things that I will say that I don't understand very well myself. The whole point of doing basic research is that don't understand what we are doing. That's why it's fun. But interrupt me, ask questions. You are very welcome to do this. And also, of course, in the afternoons, feel free to. Yeah, there's of course mathematicians that agree with this. They understand everything they do. But they understand very little. Okay, so what is the background of these tensor networks? It comes from the field of quantum information theory. So the field of quantum information and quantum computing, which came into place somehow at the end of the 90s. What it brought with it is actually a new language, a new kind of set of tools to describe correlations between systems. Namely, it gave rise to this to a pretty kind of thorough study of entanglement. Okay, an entanglement is nothing more than correlations between quantum correlations, but at the end it's just correlations between quantum systems. So the reason that people were very interested in entanglement is that you can actually prove that a quantum computer would kind of have no quantum advantage at all if it would not kind of exhibit lots of entanglement. So if there would be no entanglement, it would not have any advantage. And that's why somehow people say, aha, that means that entanglement is an interesting topic to study, because it's probably the resource that gives rise to the power of a quantum computer, and that's still a big mystery actually. What is it that makes a quantum computer so more powerful than a classical one? But anyway, so this gives rise to a new language in terms of in which you could describe correlations, and then a very natural step is to go to the quantum many-body problem and start seeing whether this language is useful, and that's exactly what basically this field of tensor or quantum tensor networks is about. And probably in the long term, this seems to be the kind of, from the theoretical point of view, at least in physics, the most real progress that has been and will be made in this field of quantum information theory. So because also it turns out that many questions in quantum information, like the stability, like if you would like to make some. You want to study error correcting codes, because your system, your quantum computer is very susceptible to noise, and you want to make it, you want to kind of protect it against noise. You have to make something like error correcting codes, and it turns out that these error correcting codes have lots of similarities with topological phases of matter. So if you start studying quantum computing and dig a bit deeper into error correction, all this, you see that actually the physics that you have to solve you have to study is completely equivalent to the physics of gauge theories, of spin glasses, all the kind of many beautiful concepts in theoretical physics naturally pop up there, and there's no escape. You have to deal with this. Anyway, that's where these tensor networks come out. But what is the motivation for actually looking at? So why do we need basically something like a new language for tackling the quantum many-body problem? Is the reason is that there's many cases in theoretical physics, or certainly not just in theoretical physics, but in physics in general, where the quantum many-body problem is still completely unsolved. And this is typically the case when you have very strong correlations, where you have strong interactions. And So the usual way of doing many body physics, both in the quantum, but of course there's always kind of an equivalent classical counterpart to it but let's stick to the quantum many body problem. So typically is that you make some kind of a good guess of some field, some Hartree-Fock state. This is exactly what people do in quantum field theory. They start with some free theory that is supposedly a good kind of gets already quite a few of the features of your system, and then you start doing perturbation theory on top of that. Okay, and then you use the machinery of Feynman diagrams and so further to see what basically the effect is of the interactions in the system, and then you're able to kind of really get lots of insights. And this is extremely successful in many cases. So like in many cases, this has been really kind of the problem of choice. But so what happens in the from the point of view of wave functions, if you look at this thing, so these Hartree-Fock wave functions are always kind of defined in quantum space. If you have like a big lattice system with some translation invariance, then it's natural that actually the optimal, the basis, the wave functions or the basis in which you will work will actually be in momentum space. So if you have, if the interactions are not strong, then momentum space is the natural basis to work in. But if you have, but think about something like the Hubbard model. I will be more precise later for people that are not familiar with this, but think about the Hubbard model. This works extremely well if indeed the interactions are very small. You start with basically your plane wave basis and then do some perturbation theory to understand what the effect is of the interactions. But at some point there's a phase transition in which basically this whole thing breaks down. Okay, so that means that actually the fiducial state, this Hartree-Fock state that you started from, was not a good starting point. Okay, there's no connection. All this Hilbert space that you build up by doing perturbation theory on top of that has nothing to do with the Hilbert space actually that you're interested in, because there's a phase transition to a different space. And if you have very strong correlations, the natural basis is typically to start expanding, of course, in the interaction basis, and then this is actually a real space. So what you want to have is in many cases some kind of a wave function that is defined in real space, and then it's basically the non-interacting things as a perturbation. But this is typically very hard. So that's why people, well, because you cannot use this whole business of free fermions and so further. So it's a very this has been one of the big challenges in many fields. So certainly, for example, this is a problem that occurs very kind of clearly in quantum chemistry. Okay, so people in quantum chemistry they want to simulate something like a molecule that is pretty large. So in many cases, actually, the correlations are so strong that the methods that they have don't work. Certainly, also, well, like in condensed matter, I already gave some examples like high TC, like the Hubbard model. This is related to high TC superconductivity. So all these things, these phenomena are not understood because indeed it is hard. I give you a Hamiltonian, and finding basically the ground state of that Hamiltonian is turns out to be hard. Of course, there's many cases where people found kind of ways around this. Like if you have the quantum Hall or the fractional quantum Hall, there's good ways of guessing somehow wave functions that are basically nothing to do with indeed these Hartree-Fock states, but nevertheless you can kind of build on them and you can kind of make these Laughlin states and so further. And so these tensor networks are supposed to give you a systematic way of constructing such states. So of course correlations are so in statistical, typically in classical statistical physics, if you have such strong correlations, the way to kind of go around it is of course using Monte Carlo. Okay, so you just sample your system, and if you're lucky, you will kind of your metropolis or your whatever Monte Carlo algorithm will thermalize quickly, and you will be able to basically get information out of the system. But in the quantum case, this approach doesn't work in many cases, exactly because the fact that there's a sign problem. Okay, the sign problem is whenever you have fermions or you have some frustration, or there's many cases in which this technique does not does not work. And of course, another kind of area in physics where these problems are kind of very prevalent is in high energy physics. No? If you kind of look at kind of strong coupling and QCD and so further, it's all about the problem is exactly that we don't really know how to deal with, how to kind of come up with a good description of the vacuum of the theory. And me at least, because my background was certainly not many body physics. One of the things that I never really completely appreciated until kind of you start doing it is that is this fact that people always are obsessed by ground states and the vacuum, because the vacuum at the end, what is the vacuum? The vacuum is nothing. No, it's really there's nothing there. It's the absolute emptiness. Nevertheless, people are always saying that this is what you need to know. And indeed, somehow, once you start looking at this from the point of view of these tensor networks, as you will see, it makes perfect sense that indeed the vacuum is the hardest thing to have. Once you have the vacuum, once you have the information about what the ground state of your system is, all the other information comes out, for the low energy at least, energy physics at least, is popping out very naturally. Actually, all the information about the low energy physics is already encoded into the ground state, which is very peculiar. No? So if you would take a random Hamiltonian and I give you one eigenvector, namely the eigenvector corresponding to the smallest eigenvalue, that doesn't give any information about the other eigenvectors except that they are orthogonal to it. Okay, that's for a random matrix. But the fact that we can actually do physics is that this Hamiltonian, or this matrix that is represented by a Hamiltonian in a physical situation is very, very different from a random matrix. Namely, it's a sum of typically local terms or terms that decay very fast. And it's the locality of your interactions that actually allow you to, that will enforce indeed that once you know the ground state, you will know everything else. So it's really, so what you immediately see is that locality of the Hamiltonian is the key in understanding actually the quantum many-body problem. And that's one of the reasons that you immediately see that indeed momentum space is not always natural. Because if you kind of take a local Hamiltonian in space and you kind of go to the momentum basis, then it actually becomes completely non-local. Which is not a problem if you have a non-interacting theory, because you can use all the kind of computational tricks, or you can just deal with free fermions or free bosons very easily. But from the moment you have interactions, then things become very hard. So we want to really kind of build up something from real space, and that's well, I want to give you some motivation for doing this today. But anyway, before doing this, let's take a step back and try to understand what we need to have interesting many-body physics. Okay, so what are the ways, or why is it that many body physics or statistical physics and quantum many-body physics is so fascinating? What are like some of the basic ingredients that you need to have to make it interesting? And as far as I know, maybe I'm limited in my imagination, but I typically see three towards somehow having interesting many-body physics. So on the one hand, you could have something like, so what you need is a competition between different terms. You need a competition between, let's say, entropy and energy. Okay, that's exactly all the interesting classical statistical mechanics is exactly like that. No? I give you kind of basically something like the Xxe model in 2D, and I want to kind of understand the thermodynamics of that classical system. Well, we know that basically the equilibrium state of that system is given by the state that minimizes the energy for given temperature. So I kind of basically want to minimize the energy minus T times the entropy, and that competition, depending on this T, whether this T is small or large, will give rise to completely different phases. If indeed T is very small, you don't care about the energy, but if T is very large, you don't care about the energy, you only care about the entropy. And this competition, it's clear that if you make the energy extreme, well, then the entropy will be very small. If you have like an Ising ferromagnet, if all the spins are up, then the entropy is zero. Okay, so it's clear that these two requirements, having maximal energy or minimal energy and maximal entropy, they compete with each other. Okay, and the temperature is exactly the kind of the number that tells you how important is one versus the other one, and that's how you actually get the interesting, basically the interesting physics. No, it's a competition. It's some kind of like a frustration, and that's what gives rise to all the physics that you all know. So a second way of getting into physics, and this is still classical. So this, of course, is the temperature and energy is both quantum and. But let's imagine that this is a purely classical phenomenon. So there's also a second classical way of getting interesting physics, and that's by having frustration. Okay, so you could have something like an Ising or a Heisenberg antiferromagnetic Hamiltonian on a frustrated lattice. Okay, so you take a triangular lattice or a Kagome lattice, and you kind of put somehow spins there, and you want to be such that actually you cannot never satisfy all the constraints. So if you would have like a triangle and you want everything to be antiferromagnetic, that's like an Ising model that is antiferromagnetic. You cannot have spin up, down. Well, the third spin will kind of not be antiferromagnetic with one of the other ones. So that there is some type of frustration. And of course, the most famous of these models is this is actually the physics of spin ice. Okay, so the first one, I think, as far as that I understand, at least, that was that observed this very well or described this in a systematic way was Pauling, who understood that indeed, if you kind of look, you just look at ice, you cool water down to absolute zero, and you do some measurements. Some people have done experiments, and they were measuring basically the specific heat, and then you can calculate basically the entropy of that ice if they cool down the temperature to zero. You see that actually this entropy doesn't go to zero. Okay, so that comes to, because if you have ice and it's you put it in a pyrochlore lattice, basically, so some type of ice is in a pyrochlore lattice, there is indeed something like a frustration, or there's actually many possible ways of arranging your H2O atoms in that lattice in such a way that you will kind of get the minimal energy configuration. So there's no unique energy configuration. There's actually exponentially many different configurations that would give you the same energy, and that means that actually at the end this whole system is behaving like something like a Coulomb gas. There's some non-trivial gauge fields appearing, and indeed so this gives rise to power law decay of correlations and so further. So this is all as a consequence of this frustration of systems, such that actually even at zero temperature you actually get infinitely or kind of exponentially many possible configurations that give rise to some non-trivial entropy and therefore give rise to non-trivial correlation. Okay, so this is the second way. So you have thermal fluctuations, frustration, but then of course there's another way of getting very interesting many-body physics, and that's just by introducing quantum fluctuations. So if you write down a Hamiltonian, so the simplest Hamiltonian that you can imagine is, for example, a classical Hamiltonian, but it's kind of on a system of spin 1/2. You just write down a magnetic field. Okay, everything will be polarized in the x direction. But then you add something like a term. Okay, so I'm assuming now that I have a linear chain, and I have basically a magnetic field that wants all the spins to be point in the plus direction. But then I add something like an interaction between the ZZ, such that I want actually the spins to point in the same direction versus all both up or both down. So certainly these terms don't commute with each other. Okay, so the magnetic field doesn't commute with somehow this interaction term, and it's the fact that you get indeed somehow two terms that don't commute with each other is equivalent to saying that indeed you get frustration. Okay, and it turns out that actually the physics of this model is in many ways equivalent to the physics of the classical Ising model, where you have a competition between energy and entropy. Actually, this is so maybe it would be better to actually add this lambda. Well, this lambda would basically be the temperature, and this would be the energy of the classical Ising model. And indeed, you will see, and this is actually what I would like to kind of give you some picture of that indeed this is actually nothing more. There's even a much more this resemblance goes much deeper. So the fact that we have a frustration between, I want basically to have all my spins and pointing in the same direction, all spins up or all spins down, to point my spins in an orthogonal direction, that this is equivalent to saying, look, I want to minimize my energy, and this is basically entropy. Okay, and this lambda is a parameter that will will control this kind of thing. So anyway, so you have a Hamiltonian of that kind. Okay, so so this would be let's assume that this is spin 1/2. This is called the quantum Ising model. It doesn't really matter whether it's in 1D or in 2D or whatever dimensions. You can always assume that something is similar. But I want to give you some intuition about the properties of the ground state. Okay, so you're interested what is basically the state that will have minimal energy with respect to this Hamiltonian. Okay, so I want to find basically the state psi such that, so this is my Hamiltonian H. I want to minimize this over all possible wave function psi, the energy. And you immediately see that actually one of the great features of a Hamiltonian like this is that actually this energy, assuming that, well, this is a translation system, let's actually assume that it's an infinite chain. This is nothing more than n times with, or L times, well, L would be the length of the chain, but L goes to infinity times the trace of the reduced density matrix times Zi, Z between, let's say, I and I plus 1, Zi plus 1 plus lambda times Xi. Okay, because if your system is translation invariant, you're guaranteed that actually the extremal eigenvectors. So if you have it's basically linear algebra. If I give you a matrix with a certain symmetry, for example, this has translation invariance, then the extremal eigenvectors, or at least the subspace spanned by the extremal eigenvectors, has the same symmetry. Okay, that's exercise if you've never done this to prove. You can prove this in one line. So that means that indeed the wave function that corresponds, if the ground state is unique, the wave function that will actually minimize the energy will be translation invariant, and therefore actually the energy is just dependent on the local reduced density matrix. Okay, so just look at one local reduced density matrix, and that's basically enough to determine the energy. So what you're interested in the ground state, so the ground state in some sense doesn't care about correlations. Okay, so the fact that indeed this model is interesting and actually has a phase transition and kind of exhibit critical correlation functions, all of this is in some sense only a consequence because you need to get these long-range correlations such as to minimize the local energy. Okay, because there's no long-range correlations here that kind of would affect the energy. It's just that turns out that to kind of get an extremal local reduced density matrix, you need to have actually these long-range correlations. So so it's really the local physics that drives basically what your wave function has to be. So that means that at the end, to find the ground state, you basically want to get a feeling what are the possible states that have extremal local correlations. The same have this particular case, if you have a system that is translation invariant, you want to have a translation invariant symmetry. Wave function must be translation invariant, but nevertheless you must have some local reduced density matrix that is extremal. And here you already start seeing, the people that are a bit familiar with quantum information theory, that there's some interesting competition. So like if you would take something like a Heisenberg model. Okay, instead of this model, you can also take the Heisenberg model. Let's kind of take the Heisenberg model. So for me, the Xi's and Zi's are just the Pauli matrices. Okay, so these are spin 1/2 Pauli matrices. So Xi plus 1 plus Yi plus 1. And let's actually take something like a little bit sophisticated model. This is called the Xxe model, where I kind of allow this delta to vary. So this is my Hamiltonian. And if delta is 1, this is actually the Heisenberg antiferromagnet. Okay, and the ground state of that model is actually the singlet. Okay, so you can easily see that the ground state of that model, if you would write this down for 2 spins, okay, this matrix is nothing more than 1, 0, 1, 1, 0, 1, up to an identity. So if you kind of just look at 2 spins, the ground state of that model would be, well, this is crazy, this has eigenvalues 1, 1, and this matrix here, all the rest is of course 0. This matrix has eigenvalues 1 and minus 1, and the part that has minus 1 here is actually corresponds to the singlet, so this would be spin up, down, minus, down, up. So this, or 0, 1, minus 1, 0, this is basically the state that minimizes the energy of that local Hamiltonian. So you want to see, so what you want is in this particular case that this reduced density matrix looks as much as the singlet as possible. But you immediately start seeing that entanglement plays a role because this is a maximally entangled state between two spin 1/2s. Okay, so what I want is that the ground state of this system is such that if you would draw all your spins, so you said this is a singlet, this is a singlet, this is a singlet. So you would actually you would want that all the reduced density matrices everywhere are singlet. Yeah, but of course, if the system is translation invariant, then all the local reduced density matrices are equal to each other. No? So the reduced density matrix of I plus 1 should be equal to the one of I plus 1, I plus 2, and so further. So, and also, of course, this wave function is defined in a Hilbert space that is exponentially large. Okay, so in principle, you cannot write this down. You have no idea what this is. There's no way of writing this wave function down in any reasonable way, while this is just a 4x4 matrix. Okay, so the problem is basically to find ground states is exactly to find what are basically the conditions that these reduced density matrices have to satisfy. How can I actually find what is the allowed set of possible reduced density matrices if I indeed impose translation invariance? And this is actually something that is well studied in the field of quantum information theory, and this is related to something that's called monogamy. Monogamy of entanglement. Okay, this is a problem indeed. Like a Heisenberg model, I wanted to have a singlet between these two, but I also want to have a singlet between these two. And that doesn't work. I cannot be maximally entangled. This part, it cannot be maximally entangled with its left and its right neighbor. It can only kind of share half of the entanglement with the left and the right. And then this one also has to do this and so further. So what it happens is that this monogamy, so the fact that a singlet, you cannot be maximally entangled with all your neighbors gives rise to actually this is exactly what gives rise to this frustration. So the frustration here is between local reduced density matrix to be as close as the singlet, and at the same time, I want my full many-body wave function to be translation invariant. Okay, and again, there's some kind of a frustration here. And you see that actually the higher the dimension you start working in, because this is one dimension, but if you would do this in a two-dimensional lattice, okay, so you would have like a square lattice. And I have the Heisenberg antiferromagnetic Hamiltonian. I want a singlet here, I want to have a singlet here, I want to have a singlet basically everywhere. Well, it means that you have to share entanglement with more and more and more people. And somehow, if you have to share with infinitely many, then you cannot have anything anymore. And that's actually the origin of the fact that mean field theory is exact in infinite dimensions. So mean field theory becomes exact in infinite dimensions because entanglement doesn't play a role anymore. Okay, because you want to have a translation invariant wave function where you kind of have indeed entanglement shared with all your neighbors. If you have infinitely many neighbors, it's not possible anymore. And that's actually the reason that in these kind of quantum spin systems, if you have like many body physics, that the lower the dimension, the more entanglement plays a role. Okay, so you want to have really interesting kind of physics that is not compatible with mean field theory. The better you work in one or in two dimensions. But there was a question.
If I understand well, this rho I plus 1 is the reduced matrix in which you integrate all the points except these two.
Yes.
But for translational invariance, you could have an expansion in which this is the first term. Then you could say I somehow integrate all the points except 3 or except 4.
Yeah, but all these terms don't affect the energy. The energy, they will not change the energy. The only thing you need to know what the energy is of your system is the 2-point correlations. Because the Hamiltonian is only, if it's a nearest neighbor Hamiltonian, well, it doesn't, there's the 3-point function, the 3-point correlation functions don't show up in the energy. It's enough to have the 2-point correlation functions for the energy. So of course they are there. And the fact that they are non-trivial and that you will get power laws and all this is actually a consequence of the fact that you want to minimize this energy with respect. So you want to have an extremal reduced density matrix. And that's what is driving all the many-body kind of physics. Yes, and I will indeed, and this is something, I don't know whether I made this clear enough. So certainly this first talk will mainly about ground states, about somehow trying to understand what is the vacuum of your theory, or what is the vacuum of your quantum field theory, or of your spin system, or of course our thermal states is something very similar. Thermal states in a classical stat mech is very similar to basically ground states in the quantum setting. So this talk certainly this one lecture I'm certainly talking about equilibrium physics, trying to understand the equilibrium physics. What is the ground state? But anyway, so you can start playing interesting games now. You can start looking at this model, this Hamiltonian. In various dimensions. So again, I don't know whether this was clear, but this is actually an important point, that indeed the higher the dimension, the less entanglement plays the role. Okay, so if you means the entanglement plays the most role in one dimension, still in two it's also very important. In 3 dimensions, typically mean field theory is already pretty good, and the origin there is really lying in this fact that entanglement, or that this monogamy of entanglement. But now you can start actually getting some intuition. And this is really the intuition where all these tensor networks, or the reason that tensor networks make sense, will come out of this reasoning. That indeed the only thing that you need to do is to be able to approximate local reduced density matrix. If you have a family of variational wave functions, or of wave functions that can approximate any possible reduced density matrix, and at the same time have the right symmetries, then this will be a good variational ansatz. And these tensor networks are exactly trying to do this. They are trying to maximize basically to get extreme local correlations together with the right kind of symmetries. Okay, so let's so actually this whole way of looking at many body physics from this point of view of these sets, okay, at the end these are convex sets. If I give you a possible, so I'm interested in finding what are the possible reduced density matrices with a certain symmetry. Okay, so at the end you want to kind of characterize these possible convex sets. So it turns out that actually something like that had already been done by the very kind of founders of the field of statistical physics and thermodynamics, namely somehow these are Gibbs and Maxwell. So what they did is something very similar to this. Okay, so they try to understand. Look, let me take any possible probability distribution. Okay, and let's try to basically look at the marginals of this probability distribution. Let's try to kind of plot all possible energies versus volume versus entropy. Okay, so I'm just taking any probability distribution. This is classical statistical mechanics, and let me plot basically for every probability distribution. There is I associate one point in a 3-dimensional kind of volume. Namely, I plot basically the energy of that with respect to some Hamiltonian. I plot basically the entropy, and I plot the volume. Okay, so of this system. So I mean, any probability distribution gives rise to a point. You start kind of take all possible probability distributions, start filling basically a volume, and at the end what you end up with is a convex set. So actually you have to take the convex hull of that volume. Actually this is describing water. And it turns out that this is the right way of understanding basically phase transitions. So phase transitions in that kind of picture will have to do with the parts in that convex set where the convex set is discontinuous, where there's some non-trivial kind of things happening, namely that where exactly where you have to take these convex hulls is exactly where the phase transitions of your system will occur. Okay, and they use this to great kind of with great success. The really cool thing, so and this is kind of forgotten. So you can read this in the original papers, but then people have kind of you don't see this in any statistical physics book anymore. These kind of pictures, because what people do is actually plot somehow the dual variables, namely they plot kind of pressure versus temperature and all these kind of things, but these are properties that are only defined for the equilibrium case. Okay, these are actually the properties that are dual to this, namely, turns out that all the extreme points of that convex set are exactly somehow corresponding to the quantities, the energy, entropy, and volumes of some thermal states, of some Gibbs states. Okay, so this is actually the more, so this is the more useful, from my point of view, this is the more useful picture, because we're interested in finding basically all possible reduced density matrices. Okay, so let's do this for this Heisenberg model that I plotted here, x plus y plus delta z. Okay, let's do this in for a one-dimensional system. So if you have one dimensions, so there's no pointer, but it doesn't matter. So if you do this for a one-dimensional system, for a zero-dimensional system, just two spins, you plot basically what are all the possible expectation values of zz versus all the possible expectation values of xx. And because of the symmetry, the expectation value of yy has to be equal to xx. And what you see is that you basically get this triangle. That's a very easy exercise. This outer triangle, these are all the possible, basically, expectation values of xx and zz of a system of two qubits. Okay, take any kind of two qubit state with the right symmetries, plot somehow what the expectation value, it will lie somewhere in this triangle. Now you can say, okay, let me actually, instead of in zero dimension, let me now impose that actually there has to be the reduced density matrix expectation value of a system that is translation invariant. Okay, so it's a one-dimensional system, and I want now to find basically what are my extremal possible reduced density matrices for that system in this coordinate space xx and zz. And what you see is that you basically get this, you get still this, but now you get this kind of shaped form. So that means that this point, for example, is not part anymore of the convex set. Okay, so this part was actually the singlet. And you see that the ground state of the system is not the singlet. So the reduced density matrix cannot be the singlet anymore, because we already saw we cannot have a singlet between 1 and 2, and also a singlet between 2 and 3. So instead of this point, you kind of jump there. It turns out that this is the ground state of somehow, this is the reduced density matrix that corresponds to the ground state of the Heisenberg antiferromagnet in 1D. Okay? And by changing this, basically this competition between xx and zz, you basically start shifting this curve, and you can immediately see that indeed somehow all these different reduced density matrices here correspond to all the possible ground states of that one Hamiltonian that I have here with respect to the values of delta. Okay, so and so this is zero dimension, one dimension. You can go to 2 dimensions. And then, of course, there's no, so how did we obtain this curve, this blue curve? It's really, this is already, actually, it's not an easy calculation. You have to really go to the beta ansatz. Okay, so you have to know about beta ansatz, because then you know exactly what are the possible ground state energies with for any possible delta, and then you have to do something like a duality transformation or a Legendre transform, and you get indeed this blue curve. Okay, so the important thing is that this is still a convex set, and all the extreme points of that convex set correspond to the ground states. These are the states that have extreme local correlations under the condition that you still have translation invariance. You go to 2 dimensions, then you get actually this, I don't know if you can see it in the back, but there's these red dots here. So what you see is this thing shrinks, as it should be, because there's more and more conditions. And at the end, if you would go to infinite dimensions, you would get this diamond here. So we'd get this simple diamond. And this is basically the mean field theory. These are the states that don't have any entanglement at all. This would be basically, if I would define the Heisenberg antiferromagnet on an infinite lattice, these would be the ground states. Okay, so now we can start actually playing this game. The same thing for the Ising model, but the Ising model is in this respect more interesting because there's an order parameter that will emerge. So what we'll do here in this picture is the same thing. Okay, so I have my kind of expectation value of xx. Okay, I should have written down xx and z. This is just a renaming, of course. This is the interaction. This is the magnetic field. And you're asking, okay, what are all the, so I take any possible wave function of 2 qubits, and I plot basically what the expectation values of xx, of z, and of x. What you see is that, so this is actually the absolute value of x, so we get some kind of a nicely curved thing. I don't know if you can see this now. So this is like a 3-dimensional picture. So this is a project. This is a 3-dimensional picture where this is something like this, and then there's a flat piece on top of that. And then there's some nicely curved, shaped object that you have here. And it's actually, you will see actually this top plane will be interesting in a many-body context, but I cannot. But anyway, this is the possible convex set that you get in a 0 dimension for all possible reduced density matrix of 2 qubits. But now you go to the 1-dimensional. You impose now that these reduced density matrices have to be reduced density matrices of wave functions that are translation invariant in 1D. And you plot all possible reduced density matrices. And what you see is that now there's a very interesting kind of features emerging. So suddenly, somehow, this convex set is not smooth anymore. There turns out to be some critical points. There was a question?
Yes, I was wondering about the Xxe model in the previous picture. Is there a way to see the phase transition here? So going from the gap to the gapless phase?
Yeah, but that's why these other pictures actually in the icing it's clear, but actually the phase transition goes on here. So the Hamiltonian, and so all the, like you say, I have a one-dimensional system. So all my reduced density matrices must lie in this droplet here. And the Hamiltonian basically defines a line. So the delta will define basically an angle. And so the ground state will be, it tells you that this is the origin. How far can I push this line outside of the origin such that it still touches my convex set? And the distance between the origin and this point will be the ground state energy. So it's really asking, this is the way you have to say it, because the ground state, of course, it's really the minimal energy of some linear combination of this term and this term. And therefore, you want to minimize the energy. You ask, how far can I push a line with, and all the points on that line would have exactly the same energy. And that line, the slope of that line is determined by the parameters in your Hamiltonian. And all the points on that line would exactly have the same energy. And the question is, how far can I push it out so that it still just touches? That's why it's clear that indeed all the extreme points of that convex set have to be ground states with respect to a different Hamiltonian. And indeed what you see is that at this point here you have something like a phase transition. So once the slope becomes this, actually then all these points get the same energy and actually you get a kind of a mean field result. But as you will see, it's much more interesting to actually add a third axis which corresponds to okay, and No. Okay, so you play the same game now for the Ising model, okay, so Xxe, but now you add a third axis, which is basically the order parameter. But in some sense, this has nothing to do with, you don't have to know what the order parameter is. This is just what are all the possible reduced density matrices of a system that is translation invariant. You just plot for every possible wave function a point. You fill all these points, and this will form a convex set. And there's an extremely interesting feature emerging somewhere in this convex set, namely that this is a ruled surface. So at this point, so this is nicely curved here, but at this point, basically, there's something that is just a straight line. Okay, so this is something that is a ruled surface. A ruled surface is nothing more than I take some kind of a ruler and I kind of roll it over some surface. No? So what it means is that indeed here there's some discontinuity. So it's all kind of nicely curved, but at this point you get a discontinuity. And if you think about it for a minute, you will immediately see that, of course, this is the point of where you have a second order phase transition. Namely that, so what is the Hamiltonian? So the Hamiltonian, if you don't have any kind of magnetic field in the x direction, just an xx and a z, the Hamiltonian has to be, well, so there's no term in the x, so that means states with the same energy all kind of have to lie on a parallel line with this x. So all the states, so what you get is actually that all the points on this line basically have exactly the same energy. And that means that, so here there's only one point with that energy, but certainly here there's many, many points with the same energy. And this is exactly the signature for symmetry breaking. So I've never seen actually, so that's why this is statistical physics school. I think this is very cool. So these pictures. This is actually the way you can see all the possible properties of the Ising model or of any other model in a very kind of intuitive way. Namely, these are all possible reduced density matrices. And you plot somehow the convex set. And what you see is that indeed all these points have the same energy. And of course, this kind of thing that lies here will kind of correspond, if you kind of look at the x-axis, this will be the spontaneous magnetization that you will get here in your system. Again, the fact that actually this is only half of it, this is the absolute value of this x, you have to reflect this. See that magnetization is here, and certainly here you get some magnetization. And the slope at which this increases in this convex set is nothing more than, of course, this very famous exponent 1/8. All of these things are actually kind of can get this of this picture. So, yes. Yeah, there's not a real meaning to this, but it turns out that this whole line here that ends in B, this line are all product states. There's no entanglement. But what is interesting is actually this top plane. Okay, so this is something that is typically overlooked. But for this you need a Hamiltonian, namely x plus ez, but you also need to add now a term. Well, if you do it like this, I would have to write the z here and x, but I also would have to add some mu times some x. So I would also add kind of a transversal or longitudinal magnetic field. So this top plane actually corresponds to the case where lambda is 0 and mu is exactly, so where this is basically antiferromagnetic, so this would be a minus, antiferromagnetic is indeed a plus, and this is actually a 2. Okay, and you can immediately see that indeed, if I have a Hamiltonian of this kind, I want to have antiferromagnetism here. So I want my spins to point into different directions, but I want here all my spins to point in the same direction. This is actually a very interesting exercise. If you look at this Hamiltonian, you will see that the number of ground states is exponentially large, and the number of ground states is exactly given. The exponent is given as determined by the Fibonacci sequence. Okay, basically, this is an easy exercise. And so that means that indeed you have exponentially many different ground states, and that's why all this whole plane here is basically a flat thing. Okay, this has to do with the fact that indeed there's an exponential degeneracy of possible ground states in this for these particular parameters. And then all these kind of states that are lying at the end of this is something like an ellipse or an ellipse. This would be kind of doing, you start from such a Hamiltonian, this defines your Hilbert space. This Hilbert space would be the Hilbert space of basically all sequences that satisfy the Fibonacci sequence. So it would be like, you can have as many downs as you want, but if there's an up, it has to be followed by a down. That's easy. Well, this is in the X basis. And this would kind of correspond to these so-called anionic spin chains. Okay, so these would be all these kind of wave function or these extreme points of these ellipses. So it would be ground states of Hamiltonians that correspond to spin chains. But anyway, let's go further. Let's go to no, but I'm going very slow. So let me finish this thing, and then I have to jump to my matrix product states soon. But let me finish a few more pictures. So if you continue doing this and you go to infinite dimensions, you see that actually this thing grows and grows and grows. So these are basically all Russian dolls that fit into each other. Okay, the zero-dimensional case is the largest, and the one-dimensional case fits in. The two-dimensional case is even smaller. The infinite-dimensional case is even the smallest one. And all kind of these would kind of give rise to all the mean field exponents, and all the kind of physics can be understood like this. And so indeed, so here you see, for example, these three cases: 0, 1. So these are these Russian doll pictures. So all of this is just to justify. Look. If I want ground states, I'm just interested in finding extremal points. But of course, even these extremal points will exhibit all this interesting kind of physics. So, what about classical physics? Okay, so what I like about this is that it shows you that actually phase transitions and the fact that you have non-trivial many body effects is really a problem that emerges because of the non-trivial state space of density matrices or of probability distributions. It actually has nothing to do with Hamiltonians. It just tells you, look at all possible probability distributions that have some symmetry. And now plot basically the expectation value of like the spin up. This is the expectation value of two neighboring spins to have the same spin. This is basically the entropy of your global probability distribution. This would be your spontaneous magnetization. Plot just for any possible probability distributions these kind of expectation values. Fill this whole space. You will see that a convex set will emerge. And that convex set will have some non-trivial features, will have some discontinuities. And that's where somehow all the all the statistical figures, the second order phase transition, all these kind of things emerge. It's a consequence of the state space of your probability distribution. It has, in principle, nothing to do with the Hamiltonian. It's just already there, just because of the frustration of what possible probability distributions can be. And you can do this further now. So it's actually amazing. No? So if you look at this picture, it looks exactly like the one for the quantum case. So the only thing you did is exchange somehow this transversal magnetic field by the entropy. Okay, and that's exactly the computation. That's as you expect. You can do this more complicated. You can do it for the Potts model. You can do this, and then you can start seeing these kind of shapes. So this is, again, this Fibonacci type of thing. This is indeed the spontaneous magnetization. But a new ruled surface is emerging here. Okay, it turns out that here somehow there's a ruled surface actually appearing, this red thing at the back. And this is really kind of the case when, so for example, this point C, the entropy of this point C is exactly, it turns out to be exactly the free energy of the spin ice model that LEAP solved. Okay, why is this? Well, if you kind of think a little bit about this, it takes a few minutes to kind of think. But what would be this? What is the Hamiltonian, or what is the temperature that I need to get this? Well, it would basically be this red plane would be all the states that satisfy this would kind of be states for which two nearest neighbor spins are never the same. Okay, and if you have a Potts model with three kind of possibilities, and two neighboring spins always have to be different, then you can basically go to the dual lattice, and it will tell you I have to jump with +1 or -1. So you could guess basically a spin 1/2 or a kind of a two-level system. And then you kind of, because you kind of jump here, if you go around the plaquettes, of course, you should satisfy that you just jump to the same thing. This is kind of a gauge constraint. And this gives you exactly basically the sixth vertex model that LEAP solved exactly. Okay, so this is all of this physics is basically there. You get the top plane and so further. And the nice thing is that indeed, it's all about second order phase transition. Second order phase transition is actually if you would not plot the spontaneous magnetization, if you would not plot somehow this curve, there would nothing really be interesting going on here. But we know that if you look at the Potts model, that if I have actually Q equal to 5, there's a first order phase transition going on. And indeed, you plot this convex set, and you see that indeed, suddenly there's something new emerging. There's not anymore just a ruled surface, there's a whole surface here. That means that actually this here is itself a straight line. So it's a straight line, and therefore you can immediately see that this is a first order phase transition. So that means that all these physics that you probably have seen in one or the other way in your kind of lectures is kind of summarized very clearly in such kind of a very simple picture.
Suppose I do a new field approximation. Then I compute the free energy and I plot it. It looks like this.
It will be inside. It will be so what you do is basically this is a variational method. So the convex set will be inside that kind of thing. So it would be something that is completely inside that convex set. So you would make.
Let me add one extra ingredient. I don't do a weak field approximation, in which I take only one side. I take two sides, and then I put the magnetic field on the extreme. You can do this. This is so-called, I don't know, bias approximation or something like this. Then I compute the free energy, and I get this. Am I wrong? Or
Well, I don't know. I've not done it for the Potts model with Q equal to 5, but I would be surprised that you get actually so what you will not get right is actually these mean field exponents. So these exponents here, no? So for example, this exponent, you will not get it right, no? So what it will be is it will be like this. It will have an exponent like 1/2 instead of 1/8. So and of course you can have this because it's something inside that convex set, but the true kind of exponents are given, of course, by this. So of course, so you could ask, how do you? So why have I never seen these pictures? Okay, so this is one of the questions you can ask. Why is it that if it's so simple to plot this, why do people not do this? Actually, to make this kind of pictures, it's very hard. You have to basically solve. You have to minimize so you have to basically find the probability distribution that corresponds to this extremal eigenvalue and then calculate, which is easy because these are classical stat-mech models. So all the extremal points of the convex set are guaranteed to be Gibbs states. with respect to terms in a Hamiltonian that have basically, well, that have Z, like interaction term, you have a Gibbs state. So all the extremal points are guaranteed to be Gibbs states, but you have to, of course, calculate the entropy and the magnetization and the energy for them. And this is something that you cannot do if the model is not integrable. And this is something that can actually easily be done using these tensor networks. So I had a student really making many CPU hours he was burning to actually make these plots using basically these techniques of tensor networks to calculate these things. But I think these pictures are, I like these pictures. Okay, so you can actually do the same thing for Bose-Einstein condensation. Okay, so this is another kind of thing that for me was always a mystery. So people say, well, the order parameter in BEC is basically just the expectation value of my creation or annihilation operator. Okay, that's the order parameter. But what does actually that mean? What does that physically mean? And here you can say, okay, let me discard this. Let me just take any possible wave function, plot the expectation value of my kinetic energy, plot basically the entropy of that density matrix, and plot this expectation value of my kind of order parameter. Plot this, and what you see is that indeed you get, again, at this point, a ruled surface which tells you, okay, this is kind of where the phase transition is going on. So that means that even if this order parameter is not physical, mathematically it's still there. This is just that there's no reduced density matrices. Something has to kind of go wrong there. Okay, so so anyway, all of this introduction was way too long, but was just to justify the fact that we are interested in finding wave functions with maximal, extremal possible reduced density matrices compatible with somehow the symmetries in your system. And we'll just build this up in terms of these tensor networks. Now we'll try to kind of find a systematic way of doing this. An important consequence of these wave functions that actually satisfy this is because, again, the only requirement is the locality. You want to have the local reduced density matrix to be extremal. It will come out that actually all the wave functions that are ground states of such systems obey something that's called the area law of entanglement entropy. So they will have very few correlations. And but let's have a 5-minute break or something. Is that good? Thanks. Whoa. My
We stop around one.
yeah, okay. I will make it short. Good. Okay, so let's continue and try to let's actually try to guess the wave functions that that will form the extreme points of this. Like, for example, let's try to guess how can we construct wave functions in this particular case for Heisenberg antiferromagnet that indeed would kind of have reduced density matrices close to this. So what you see, so I want to have reduced density matrices that are singlets, but I also need translation invariance. Okay, so let's try to make some guesses. So I have a Hamiltonian that, well, I have a spin system. For example, let's look at the one-dimensional Heisenberg antiferromagnet, and I want to have a singlet between these two and between these two. This is, for example, one possible trial state, okay, which I take just tensor product of singlets. So here the energy is extremely good. Here the energy is extremely bad. Here the energy is extremely good, extremely bad. Okay, so clearly this doesn't work because this system is actually not translation invariant. It's only translation invariant with respect to shifts. So what I need is to have a mechanism of building wave functions that actually have very strong nearest neighbor correlations, but also have translation invariance. Okay, and there is a construction that actually originates from a paper from Affleck, Kennedy, Leap, and Tazaki, which is a beautiful paper in which they basically solved some open problem that was raised by Haldane, namely in respect to the Haldane gap. But anyway, so what they kind of suggested is that such wave functions can be constructed by saying, look, maybe I have two spin 1 halves and two spin 1 halves, but let's actually let's project these two spin 1 halves to a spin 1 half. Okay, let's kind of just put a projection here that maps this 4-dimensional Hilbert space to a 2-dimensional Hilbert space. Okay, the same thing here. Let me kind of project this 4-dimensional Hilbert space here to a 2-dimensional Hilbert space. And let me do this projection everywhere. Okay, it's like saying, like, these spin 1 halves that were maximally entangled with your neighbors, they are something like the quarks of my physical spin. So my real spin consists out of two quarks in some sense that are, of course, you cannot kind of subtract it, they are underlying this, and this one is maximally entangled with this neighbor, this one is maximally entangled with this neighbor, and together somehow, because they form something like a bound state, they actually, these two quarks together only span a 2-dimensional Hilbert space. So you start really with a product of singlets and just project these singlets down to a 2-dimensional thing. And what you see is that indeed, this will give me a wave function that has actually a pretty good reduced density matrix between these two. Okay, because the entanglement, there's lots of entanglement. It's mediated by this bond here, by this singlet that is lying here. This one will also be strongly correlated with this one. And actually, by construction, this wave function is translation invariant. It turns out that you can know that this is exactly the right picture. Okay, so this is actually the way, this is an extremely good kind of ansatz. If you would make this ansatz and with this such wave functions try to kind of understand what this convex set is, you would see that you will already get very, very close to this blue curve. Okay, so and there's a systematic way, of course, of improving such an ansatz. What you can say is that actually this would be, there's no reason why my quarks, my underlying basically entities in which my spin 1 half is built up, that these are actually also spin 1 halves. I could just put a d-dimensional system there. So I could say, this is a d-dimensional system. So this would basically be a maximally entangled state of d systems, I. So this thing would be something that has lots of entanglement. Okay, that lives on a d-dimensional Hilbert space. It's a maximally entangled set of d systems. And this thing is a map. So it would basically be, if this is an index alpha, beta, and I, would be characterized by a matrix or a tensor A alpha beta that maps a d square dimensional Hilbert space to a 2-dimensional Hilbert space. Okay, so is this clear? Because this is pretty crucial that you at least get somehow a feeling of what we are doing. If not, please ask. Okay, so this turns out to be a very kind of simple procedure. Right? So it's like it's the only way actually I know to construct a family of functions that is translation invariant. Just try to do this yourself. To write down wave functions that are translation invariant. It's very hard. Okay, and so especially if it has to be translation invariant and has to be, you have to be able to basically take the limit. Okay, the only guesses that you could typically make are maybe like all spins up, or maybe all spins up and one spin down, and then the superposition of this spin down being everywhere. These are indeed translation invariant systems, but it's very hard to kind of come up with something else. Well, this construction actually does it. Is the only systematic way in which I know that you can construct translation invariant wave functions in such a way that you would need exponentially many product states to write it. So if you would write this wave function down in terms of any product basis, you can actually easily prove that you would need exponentially many. Okay, that means that it really explores already like your full Hilbert space, and it gives like non-trivial weights to everything. And it has exactly this feature that nearest neighbor correlations, because they are mediated by something that is strongly correlated here, will kind of be extremal. So they will have very strong nearest neighbor correlation functions. That's what you need for kind of having a ground state. And at the same time, they will have your translation invariance. Yes? Well, oh, okay, sorry. I missed, indeed, I forgot to mention one extremely important thing, is that, of course, this map from these two spins to my physical spin, this can be any linear map. Okay, so the number of parameters that I have here, of course, and this cannot also be not instead of a two-dimensional system, this could actually be a d-dimensional system. So the number of parameters that you have here is actually d times d squared. These are just d times d squared complex numbers. Okay, so for any possible map, so this is, well, for every alpha, beta, and I can specify a number. And this gives me basically a manifold in my huge, so we'll, actually in a later lecture we will kind of prove that this is a manifold and all this. So this will give rise to somehow a manifold, the manifold of matrix product states. That is parameterized by a number of parameters that is actually this small d times the big D squared. And if you would take any other choice of your maximally entangled state, you could indeed put whatever xij here, which is the most general way in which you can write, can actually always absorb this x into the A. Because it's a local kind of thing, no? You just absorb this x into this A, and then it's just a different matrix product state. So there's no loss of generality in indeed choosing this thing to be the maximally entangled state. Anyway, so what you get here is a systematic way of building wave functions with very strong nearest neighbor correlations and translation invariance in one dimension. And the amazing thing is that indeed it turns out that this manifold parameterizes, or is in a very precise way, in which we will kind of see later. It gives somehow, it parameterizes really the manifold of all possible ground states of local gapped Hamiltonians. So if you have like a local spin chain, like of that kind, and it has a gap, we will also kind of define, we'll be more careful with these things later, and it has a gap, then actually it's guaranteed that the ground state will be extremely well approximated by a wave function of that kind. It turns out that this is not just the ground states, even if you can, or not just the gap states, even if your system is critical, you will kind of have a very good family of wave functions. You will construct a family of wave functions that are all parameterized by somehow these tensors d, and then by doing somehow a scaling limit, when this d goes to infinity, you will kind of be able to extract all the critical, all the information that you want to have actually about critical wave functions. So even if the system is gapless, this still forms an extremely good approximation of this. And indeed, somehow the most successful ways of simulating quantum spin systems are actually nothing more than variational methods over this class of matrix product states. Okay, so these product states, they turn out to really, they basically parameterize the manifold of all possible ground states. And that's an extremely useful thing. So as I said in one of the later lectures, what we wanted to do is to kind of get an idea and an understanding what are the possible phases of matter? What are all the possible phases that cannot be connected adiabatically with each other? Well, because somehow the ground states of all these different theories must be of that kind, it's enough now to just look at this family of matrix product states and try to understand whether I can interpolate two matrix product states with each other. And that's a much simpler task than actually having to interpolate Hamiltonians, for which then for every Hamiltonian you have to find the ground state. You basically know that the ground state of such a Hamiltonian is of that kind, and vice versa. If I have such a state, which you will see later, any such state is actually the ground state of a local Hamiltonian. No, you can do that, and indeed, so this will give you better. You will have more parameters, and you will have a better approximation. I agree. But in this particular case, it turns out that this is not even needed. That actually of course, if you have your triples, it's much more complicated to start writing down. You will see that actually there's one of the features of these wave functions that makes them very useful is that you can actually, given such a wave function, you can calculate all the possible correlation functions exactly in a very easy way. Okay, if you start working with triples, it will start being much harder to actually extract all the information, to calculate basically what is the reduced density matrix, what is my expectation value of this correlation function, all this. This will be actually harder. But once you see this picture, then this in the one-dimensional case, it's immediately clear how to generalize this to actually the higher dimension too. No? So you take a two-dimensional lattice, say the Heisenberg model or the Ising model or Hubbard model or any other model that you're interested in, and you want to understand, okay, what would be somehow a good parameterization of the ground state of this? Well, in a two-dimensional square lattice, you just start with your maximally entangled states. And project them down. Okay, and project them to your physical system. So that means that in this particular case, your ground state would be parameterized by a tensor with 5 indices. Okay, 4 of these indices are basically the physical, the virtual indices, and 1 of these indices is the physical index. So what you do is basically, instead of working in Hilbert space that has a dimension that is exponentially large in the number of spins, you start parameterizing basically all these wave functions by one simple tensor. Okay, so this one tensor, and you repeat the same tensor everywhere, is kind of now somehow the ultimate order parameter for that wave function or for the ground state of that phase, because all the features of the ground state are encoded into that one tensor. Okay, and yes? So if you have a triangular system, then typically you would have a tensor and you would have like, how do you draw this? Like this. Okay, it would have 7 indices. That would be the natural. But of course, if you have a triangular lattice, so the complexity of the number of indices, this grows exponentially. The number of parameters here, it grows exponentially with the number of indices. So also the complexity of dealing with this. So if you have a triangular lattice, then it might actually be useful to go to the dual lattice, which is the hexagonal lattice. And then actually you only have 4 indices. Okay, so this is, in practice, these are trade-offs that have to be made. You can also have Kagome. But the philosophy should be clear now. So I want, if I have a Hamiltonian that's defined such that there's a term between these two, there's a term between these two spins and these two spins and these two. Everywhere you have a Hamiltonian term for which it's important that this energy is small, you put basically an entangled bond. And then you basically let these parameters play the role. You variationally optimize these parameters such that at the end you will basically find the minimum energy state within this kind of set of variational wave functions. So this would be like a square lattice in which the spins are interacting with all their neighbors. Okay, so there's a Hamiltonian term. All the nearest neighbors.
But why the central spin now is placed in 4 points?
Well, so this is basically this point. And this bond would be this bond, this one here, and this one there. So you basically, everywhere there is an interaction, everywhere you want this reduced density matrix to be extremal, you put some entanglement. So it's just that. No, because this spin can. So this maximally entangled state has nothing to do with this one. No, this is a completely different one.
So you're multiplying the central spin for time.
No. I'm starting. So the way you have to. Okay, maybe that's a good. It's good that you asked this. So the way you have to interpret this is that I start with something like a dimer state. I start with a Hilbert space that is way too large. Okay, so these are all just dimers. And then I say, actually, this 4 kind of spins here, they span a space that is d to the 4. And I just put a map on them, a linear map that maps this to a d-dimensional space. Yes.
Not really a square lattice. It's some dimer program put on the square lattice.
No, but at the end, this wave function that I define like this actually has all the symmetries of my square lattice. So it is actually a wave function defined on the square lattice, because this is just a way of interpreting what is going on. But at the end, this actually has the right. Well, to have all the symmetries of the square lattice, of course, you need also that this A would be invariant under under rotations of these indices alpha, beta, gamma, delta. Okay, but this is actually a complicated business, and we will come back to this later. This will be important in characterizing topological ordered states. Yes.
How do we know what is small d?
Sorry.
How do we know what is small d in your model?
The small d is of course the physical Hilbert space. Okay, so if I would have like a Heisenberg spin 1/2 model, then this is 2-dimensional. If I would have a Heisenberg spin 1 model, this is 1-dimensional. If I have a Hubbard model, then this is actually 4-dimensional. Okay, because a Hubbard model, then on every side I can have either no electron, I can have one electron with spin up, one electron with spin down, or an electron with spin up and down. So this would be 4-dimensional. There is indeed, because I'm talking about the Hubbard model now, there is a bit of a slight complication if you deal with fermions. Okay, so for this to be a well-defined wave function, you need, and you deal with a system of fermions, you need that your wave function has a well-defined parity. Okay, you cannot have, there's this super selection rule in quantum mechanics, you cannot have, if you have a system of fermions, a superposition between an even and an odd number of fermions. But that's actually easily dealt with by indeed imposing that this tensor AI alpha beta gamma delta actually is even. So that means that if the parity of I and alpha beta, the parity of I plus the parity of alpha plus beta plus gamma plus delta is not 0, then this tensor has to be 0. Okay, and that's easily dealt with. Then automatically this will inherit all the symmetries, and this is indeed exactly how we will kind of build wave functions with the right symmetries. Yes.
If you fix the big V, the value of big V, so that's also a parameter that you have, right? What happened in the previous one you were showing? So what is
Yes. Okay. Yes, indeed. So fixing this big D will basically be will make it variational, and therefore it will just be an approximation from the inside of that convex set. And you will be able to say, look, this is a good variational method if indeed this kind of the distance between the exact convex set and the one that you obtain by plotting only wave functions with a certain d, if these distance is very close. Okay, so this is basically, so of course if this d becomes infinity, it's easy to see every wave function can be written like this. Okay, but that's not useful. Okay, in the practice you want to have a small d, and it will turn out that indeed working with small d is enough. So let me actually give an example of a wave function that of two wave functions of that kind that is actually that are useful to deal with. So for example, the most famous state of that kind is actually called the EQLT state. Okay, so this is exactly the one that Affleck, Kennedy, Leap, and Tazaki introduced, and this is a model where my physical dimension is actually 3-dimensional, so it's a spin-1 system, and this is defined for a 1-dimensional spin chain. So I have a 1-dimensional spin chain where my physical spins have spin 1, and it's a Heisenberg Hamiltonian. I forgot the exact kind of. Maybe somebody knows. I think it's 1/3 SI times SI plus 1 squared. Okay, so because it's spin 1, the SI times SI plus 1, this Heisenberg interaction squared is not equal to this term, but this thing is still a Hamiltonian. It turns out that the exact ground state of that Hamiltonian, it's like a Heisenberg antiferromagnetic with spin 1, is of that form, and that form can be obtained by saying, look, I start with my singlets. So these are all singlets now. These things are really spin up, down, minus, down, up. And I project these things into the symmetric subspace. Okay, so what is the symmetric subspace of two spin 1/2s? Okay, so you all know you have two spin 1/2s. They transform according to SU2. Well, then SU2 times SU2 is basically you have sorry, the spin 1/2 representation times the spin 1/2 representation of SU2 gives rise to a spin 0 representation and a spin 1 representation, and the spin 1 representation corresponds to the symmetric. So the span by the symmetric subspace. So this projector here, in that case, would correspond to all the wave function of the kind up, up, plus down, down, for example, or up, down, plus down, up, and up, up, minus down, down. So these would be, somehow they would span the full symmetric subspace, and this would basically be A0, A1, and A minus 1. Okay, so these would basically where somehow this index, if I say A0, so this would basically correspond to A0 alpha beta, where this would be index alpha, and this would be index beta. Okay, so this is a very simple way, but to construct this. So, but I suggest that actually you try to play around with this a little bit yourself. So there's actually much more interesting states that can be written. No? So for example, let's try to do something in 2 dimensions. Let's try to write down something that is famous, that's called the resonating valence bond state. Okay, the resonating valence bond state is a state that was introduced by Anderson because it could be useful in understanding high T superconductivity. So what this state is basically let's do it on the square lattice. So you take a square lattice, and I want to kind of, my wave function is defined as the superposition of all possible ways in which I can put dimers on that lattice. Okay, so these are singlets on that lattice. So for example, I put a singlet like this, and I start filling this thing. Okay, so this is one configuration that is allowed. You start, and you take the superposition of all possible wave functions in which all these pairs are basically singlets. Okay, and the superposition of all these things is actually, well, it's called the RVB. And the superposition is with signs that are all equal to +1. And maybe, okay, because it's actually time, but maybe I'll leave it as an exercise. You can actually easily find that you can write this down exactly as one of these Pep's wave functions, where the bond dimension d is equal to 3. So yeah, d is equal to 3, and of course, this physical d is equal to 2. Okay, so this is not, well, it's not particularly easy, but it's actually a very good exercise to try to see. But so you see many of these wave functions that are popping up that people have been using turn out to have a very efficient description in terms of such Pep's wave functions. So also many wave functions that occur in the context of gauge theories or of topological order or of describe somehow systems with non-trivial, like the Kitaev-Majorana chain. Okay, so this chain of Kitaev that you probably have all heard of at some point is actually an MPS with bond dimension 2. Okay, so this Kitaev chain has a very simple kind of description in terms of matrix product states, in terms where you have these 2 matrices. This would basically be the identity, and A1 would basically be 1 minus 1, 0. Okay, so this 2 simple matrices, just the identity and basically I times sigma y, they kind of, with these 2 matrices, and you kind of connect them to each other like this, and you interpret this now in terms of a fermionic state. This is exactly this ground state of the Kitaev chain that has non-trivial edge modes. Okay, so but we'll see kind of much more of these later. So the take back of all this, what is the meaning, or where do these wave functions come from? They come from the fact that I want to write down in a systematic way wave functions with extremal local reduced density matrices that have some symmetry. And if you start playing this game, this is how you end up with this. This is basically the only way that I know where you kind of come up with this. And these states that you kind of get this way are called tensor networks. So it's basically a way of connecting all these tensors to each other in such a way that at the end the whole wave function is determined by one single tensor. And now the amazing thing is that you can start doing interesting physics now by just looking at this one tensor. You can start looking at different phases of matter as being, okay, what are the different symmetries that these tensors have? Okay, it turns out that, for example, the different topological phases of matter will be characterized by these states having different symmetries. And you see, indeed, this state is not just living on the physical Hilbert space, but also has indices on this kind of shadow world, or somehow the entanglement space. Okay, and it is exactly this that gives you all the power. So this tensor is basically telling you how all the correlations in my systems are routed. And that's actually why this is a very good kind of example to try to work out how to write down the RVB wave function in terms of a tensor network. It's really somehow these tensors are telling you how is the entanglement basically distributed in my system. And if you start doing somehow, if you have a phase transition, well, you see this will kind of completely be reflected in a complete change of the symmetries of this object. And that's why indeed using this language of tensor networks and in terms of entanglement, because at the end it's all about entanglement, will basically allow you to recover this whole Landau paradigm. Okay, so that the phase transitions are about changes in symmetry. Okay, these are basically the ultimate order parameters of your system. It's really the parameters that characterize all the properties, not just one expectation value. All the expectation values are just, of course, properties of this. And the nice thing of tensor networks is that you can actually also calculate the expectation values of these things. The last thing that I want to say, because it is actually time, and I'm sure you all want to kind of go for lunch, but is that all these wave functions have one thing in particular in common. And that really follows from this way that these things are constructed, and that's that they satisfy something that's called the area law for entanglement entropy. But we will kind of talk more about this in the next lecture. So thanks.